Yeah, so thank you very much for the opportunity to present our work here today. I think our group is the only group in material science department. So I hope that we'll be able to share some of the things that we do over in engineering. But next slide, please. Next slide. Just in case there are people in the audience that don't know what we work on, in our group, we generally work on the synthesis of semiconducting materials, and I don't think I need to give too much of an introduction about them. Basically, we're trying to replace traditional inorganic semiconducting materials so that we can make more lightweight devices and hopefully make flexible electronic devices in a more cost-effective manner. And the typical applications that people generally look at is to use these materials in organic light-emitting diodes, field effect transistors, and also in photovoltaic devices. So next slide. In my group, we have a combination of chemists and material scientists. So we generally start off by doing some small molecule and polymer synthesis. Half of the group really focuses on looking at the polymerization mechanisms. For example, we do a lot of work on living polymerizations for semiconducting polymers. But other times, we do more application-oriented synthesis of materials. So trying to build in specific properties into the materials and then drive them towards applications. And right now within the group, the main application that we look at is to use the materials in photovoltaics. So next slide, please. So this is kind of a messy slide, but I just wanted to put this in to highlight how far organics really have come. So these days, polymer LEDs will outperform inorganic LEDs. And also on this slide, what is shown are the champion efficiencies when it comes to photovoltaics. The blue region in the middle shows the efficiencies for traditional silicon devices. And on the bottom right-hand corner, what is shown are what's known as the emerging PV technologies. So that would include things like dye-sensitized solar cells, and then the dark round circles in orange correspond to the organic devices. And we've reached a stage where we can achieve efficiencies of around 10 to 11%. So we have seen huge advances made in this area as well. But next slide, please. And I guess I don't think the pictures have really come out very well, but these advances in performances really have come at a cost. And that the materials that we make these days, you have to do around a 10 to 15 step linear synthesis to make the polymers at all. And so the graphs on the right-hand side are showing how much the typical polymers cost per number of steps that you have to do. So over on the top right-hand corner, you can see that these days, for the high-performing materials, we would have to do 10 to 15 steps of synthesis. And that means that the materials are not cheap at all. So while many of us will motivate our work saying, oh, organics great, because it's going to enable cheaper technologies, if you think about the synthesis that needs to be done, that's really not true. Another issue is to do with the waste of material that's produced. Again, I apologize, the figure is not very clear here. But basically what that figure is showing you is that in order to make a very simple polymer such as poly-3-hexylthiophene, if you want to synthesize a kilogram of it, you will end up producing about a ton of waste, which will include toxic metals that we'll be producing as well. So while some of these issues will be mitigated by scale-up, there's clearly a need to be developing more efficient ways to make our materials. And for us, this is really where direct arylation comes into play. So next slide, please. So our starting point for this work was, at the time, we were looking at the synthesis of nonlinear semiconducting materials. Being a material science department, we're interested in making structures that haven't been created before, and then do a structure-property relationship study. So specifically, while many nonlinear insulating polymers have been synthesized before, nonlinear semiconducting polymers really haven't been synthesized because the synthetic techniques are cumbersome. So we really wanted to see how the topology of semiconducting polymers will alter the optoelectronic properties of our systems. So with that in mind, like the nonlinear polymer architectures that you can think of, for example, would be hyperbranch polymers, star polymers, and dendrimers. Next slide, please. And just to show you, there definitely have been examples in the literature where people have made these nonlinear systems. So in this particular review, these oligothiophenes were highlighted. But as the title of the paper suggests, all of these are oligomers, so no one had really made polymers. And in order to make these oligomers, what you have to do is a very tedious stepwise synthesis, where you start off with your monomer, you halogenate, you next do a cross-coupling reaction, purify the material, and then halogenate, purify, so on and so forth. So making these materials are very, very tedious. And next slide. And some people have really gone as far as making a huge systems. But again, here, this was done using a stepwise synthesis. So moving on, next slide, please. What we wanted to do was to try and make a hyperbranch polymer using a one-step reaction instead of doing this multi-step tedious synthesis. So next slide, please. With this in mind, we started digging around in the literature, and I just want to highlight that this work was performed with a Michael group here at the University of Washington. So specifically, we looked at this paper that was published a few years ago in JACS, where they had taken 2-bromo-3-hexylthiophene and polymerized it using direct arylation using a palladium catalyst. And you can see from the table on the right-hand side that they were able to achieve fairly good results. They obtained high molecular weight polymers, and the residual regularity of the polymer is very good. But we were actually more interested in the results where a low residual regularity was obtained. In this particular paper, they explained the low residual regularity to head-to-head coupling that you might see in the polymerization, but we wondered if their interpretation of the results were true. So next slide, please. So specifically, when we're actually looking at the residual regularity of something like P3HT, what we focus on is the NMR peaks in the alkyl region between around 2.4 ppm and 3 ppm. And so if you look at that region, you see two peaks coming up there. And the peak on the left-hand side corresponds to the desirable coupling that one would typically need, where you have the head-to-tail coupling. But then the peak on the right-hand side at about 2.6 ppm, that corresponds to the head-to-head coupling. And usually by looking at the ratios between the two, that's how we calculate our percent residual regularity. But looking at this reaction here, we wondered, well, maybe this head-to-head coupling was actually being misinterpreted. And by which I mean, if you go to the next slide, we wondered if that peak actually included coupling that could take place if you couple through the 2 position and the 4 position of the thiophene, or in fact, you actually had coupling occurring both at the 4 and the 5 position of the thiophene. So because we had these questions in mind, we decided to do the reactions ourselves and also try alternative conditions as well to see what results we could get. So next slide, please. So on this slide, I'm showing you just 2 specific conditions that we tried, and you can see the different NMRs on the bottom. And in addition to the 2 peaks that I talked about, which correspond to the head-to-tail coupling and the head-to-head coupling, what we started to notice was this additional 3rd peak coming into play. And you can see that the ratios between the 3 peaks really do vary depending on the exact conditions that are used in the polymerization. So next slide, please. And the actual analysis of the polymers trying to determine the exact structure that we had was actually very, very complicated. And we had to make a number of different model systems in order to elucidate this. But eventually, using the NMRs, we were able to calculate the degree of branching that we had obtained using the different conditions. And specifically using what we're calling condition A here, we obtained a degree of branching of 10%. Similarly, for condition B, we obtained a degree of branching of 40%. And using viscosity measurements, you can also estimate the shape of the polymer that you have, specifically using the Markowing equation and calculating the alpha constant. If you have a low alpha constant, that means that you have something that's more spherical, so it means that you have more of a dendrimer structure. But if you have a larger alpha constant, then that corresponds to a system which is more stiff. And so looking at the alpha values for condition A and B, we obtained a value of 0.31 for one system and 0.19 for the condition B. And that makes sense for the NMR analysis as well, and that if you have a larger degree of branching, we should have a more spherical polymer. So the viscosity measurements really confirm the structure of the material that we had. The next slide. Using the NMR analysis, we were really able to figure out the exact polymer structure that we had. And so you can see, especially for the bottom left, we're getting pretty close to something that resembles a dendrimer. And just to point out the color coding that we have, the green corresponds to the dendritic points that we have in the polymer. And then anything that is highlighted in yellow corresponds to the 2,4 coupling that we were seeing on the thiokine, whereas if it's not highlighted, then it means that we were getting 2,5 coupling. And next slide, please. And by really tweaking the actual ligands and the conditions that we used for the polymerizations, we were able to really start to control the degree of branching that we were getting in these polymerizations. And next slide, please. What's exciting for us as well is that depending on the degree of branching that we had, we really saw very different optical properties, in that the UV vis absorption would redshift with increased degree of branching, and our materials became more fluorescent with increased degree of branching. So for us, this was a great result because we could synthesize a hyperbranched polymer in just a single step, instead of doing these multiple halogenation and cross-coupling reactions that other people have done in the past. So next slide, please. But given that, there is still a problem in that, as I mentioned, the yellow parts highlight the 2,4 coupling that's taking place. And for a semiconducting polymer, having that kind of coupling is actually detrimental to the performance of the material because it means that we don't have any conjugation through the system. So the fact that we were getting this at all was a problem, and it became readily apparent that we needed to be doing better in doing our polymerizations. So next slide, please. So this is really more of a tutorial slide for those who don't work with polymers, trying to summarize the two main ways that we make polymers. So most pi-conjugated semiconducting polymers are synthesized using things like Suzuki coupling and Stille coupling reactions, and that means that we have a step growth mechanism going on. So in this case, you'll start off with just a random mixture of monomers. Two monomers might react together to form a dimer, and then from then onwards, the reaction is very random. A dimer might react with another monomer, or it could react with another dimer. And eventually, if you have enough of these couplings taking place, ultimately you'll get a polymer. And as I mentioned, this is the mechanism that most polymers are molecular weight distribution. Second problem that we have is that the molecular weight is heavily dependent on the purity of the monomer that is used. So that means that we always see a lot of batch-to-batch variation. So even if we think we're making exactly the same material, it's very likely that it'll show very different properties based on the molecular weight differences that we see. And ultimately, if we're trying to use our materials in electronic devices, this fluctuation is very problematic. So instead, what we'd really like to have is what's known as the chain growth polymerization, where you start off with an initiator species and you add one monomer at a time to this growing polymer chain. And if you are able to control the kinetics of the polymerization, then what you end up with is what's known as the living polymerization, where you can target specific molecular weights and also be able to produce the polymer with low molecular weight distributions. So if we're developing materials for electronic device applications, it would be much better to have a living polymerization. And a huge part of the work that we do in our research group is related to developing a living polymerization for semiconducting polymers. So next slide, please. This slide is just summarizing the typical procedure that's used to synthesize poly-3-hexylthiophene P3HT. Typically, you would start off with a 2-bromer 5-iodothiopene, add a Grignard to this reaction. The iodo will react more readily, so you form a Grignard on that side, and you add a nickel catalyst. So basically, you're doing a Kamada coupling reaction multiple times to end up with your polymer. And just quickly going through the mechanism, it's thought that the reaction begins by 2 transmethylations occurring with the nickel. So you form a bithiophene species with the nickel in the middle. The nickel then reductively eliminates. And for a long time, it was assumed that this nickel 0 species would diffuse away into the solution. And if that was happening, then the nickel could reinsert into any carbon-bromine bonds, and that would actually result in a step growth polymerization. But the people who were doing this work, what they realized was that whenever you did this reaction, you ended up with a very narrow molecular weight distribution, and that the molecular weight was always proportional to the monomer to catalyst ratio that was used. And also, unusually for semiconducting polymers, they would always end up with very well-defined polymer end groups. So based on these results, what people speculate now is happening is that the nickel never really truly leaves the growing polymer chain. It keeps working along the same growing polymer chain by making pi-aryl complexes with the thiophenes. So we do this reaction a lot in our group, and we've really used this as a workhorse reaction in the group. But looking at this, we wondered, well, can we use direct arylation in the synthesis? So next slide, please. So specifically, could we start off with a 2-bromo 3-hexylthiophene instead and do a direct arylation and still be able to do this living polymerization? But the problem that we had is, well, firstly, we ideally wanted to be able to use a nickel catalyst because in the Kamada catalyst polymerizations, it was known that the nickel provides the best degree of control during the polymerization. But unfortunately, in the literature, there's really very, very few examples of nickel being used to activate the CH bond. There's more examples of palladium for direct arylation, but unfortunately for polymerizations, it's been shown that you don't get the same degree of control as you would when you use nickel. So next slide, please. So at this stage, we wondered, well, could we decouple the 2 steps? Could we do a CH activation using one methyl and then follow up to do the polymerization with a second methyl? And at this stage, we paid our attention on using gold because there was actually literature precedence for activating a thiophene hydrogen bond using gold. But the key thing here was we needed to have the first step be catalytic too, in that if we had to use a stoichiometric amount of gold, then there would be no benefit. We might as well just go back to using the magnesium and then do a Kamada coupling instead. So next slide, please. So what we really wanted to achieve is what's summarized on this slide. So by using a catalytic amount of gold, activate the CH bonds, hopefully the resulting organic gold species would then transmethylate with either a nickel or a palladium, and then be able to grow the polymer chain in a controlled manner. But basically, to achieve this, there are 2 challenges. First of all, we needed to make sure that we could actually activate the CH bond using a gold-1 species. And then secondly, we needed to make sure that the transmetallation from gold to either a nickel or a palladium would actually take place. So in order to test this, we did two test reactions, first of all. So next slide. We first of all wanted to make sure that the CH activation really did take place. So one of the ways that we did it was to use the gold-1 species shown on the bottom half of the scheme. We also tried to make the same species using standard Grignard conditions, just to confirm that whatever we synthesized was the same thing. And if you look at the NMR on the bottom right, specifically in the aromatic region, you only see one singlet there, which would correspond to the thiophene proton. Next slide, please. So having confirmed this, we then went on to try the polymerizations. And this was a big struggle. Initially, when we started off doing this work, no matter what nickel catalyst we used, no matter what solvent, no matter what temperature, we really couldn't get this reaction to work. But next slide, please. So at this stage, we decided to try different palladium catalysts. And finally, we were actually able to identify some combinations where we could actually obtain a polymer. And right now, this reaction works best when we're using Pepsi as a catalyst in the reaction. So next slide, please. And this is really just summarizing the type of polymers that we're getting right now. The individual peaks show us that we're getting polythiophene with HH termination, so the X would correspond to a hydrogen. And when we look at the molecular weight distribution, specifically looking at the dispersity, we're getting values of about 1.4, which is imperfect. When we do our standard Kumada polymerizations, we get a dispersity of 1.1. But then nevertheless, this is an encouraging result. And that standard step growth polymerizations usually would give you dispersities somewhere between 2 and 3. So next slide, please. But we are actually still stuck in the sense that, as I mentioned, what we really would like to be able to do is to use gold catalytically right now. And the polymerization result that I just showed you uses a stoichiometric amount of gold. And one of the problems here is that whenever we add base to the actual polymerization, at this stage the polymerization ceases to work. And in order to prevent, so this is basically driven by the fact that the formation of the gold base bond is very weak. And so in order to overcome this, we've tried things like adding extra halide into the polymerization mixture, because we know that the transmetallation is driven by the formation of the gold halogen bond. But then when we add extra halide, then the CH activation no longer works. So we have a problem in that the anion that's required for the CH activation does not work for the transmetallation and vice versa. So we're really trying to figure out if there is anything that we can do in order to get the two steps to work effectively moving forward. But hopefully, fingers crossed, we'll have a solution moving forward soon. The next slide. In just the last couple of minutes that I have, I just want to give one slide updates of other projects that we're working on in our group related to trying to achieve a controlled polymerization for these semiconducting polymers. So specifically, as I mentioned, we ideally really want to be able to use nickel as a catalyst for our polymerization. So we're often on the lookout for examples where CH activation has been achieved using nickel. And a couple of years ago, the Itami group published an example of using CH-CO coupling between oxazoles and aryl triplets in order to achieve a coupling. So what we're doing right now is basically making the monomer version of this and trying to achieve a polymerization instead. So that's one project that we're looking at right now. And moving to the next slide. Another project that we're looking at is to do with CH-CH coupling. So ideally, in order to synthesize high-performing semiconducting polymers, what we'd like to have is an alternating donor-acceptor system where you have an electron-rich monomer and an electron-withdrawing monomer right next to each other. If you have this alternating copolymer system, then you can synthesize low bandgap polymers, which work extremely well in photovoltaic devices. But usually, in order to synthesize these, what you would take is you would halogenate one of the monomers and then make the organometallic species of the other monomer and then do a standard cross-coupling reaction. But what we'd really like to be able to do is to do a CH-CH coupling where neither of the monomers is functionalized and yet still be able to do the polymerization and obtain an alternating copolymer in one single step. So next slide, please. So we're definitely working hard towards this goal. Specifically, we're looking at an example of trying to copolymerize thiophene with an electron deficient system. And we are starting to get these copolymer systems, but one of the big problems that we're having is the homocoupling that the thiophene undergoes. So moving forward, what we're trying to identify is a catalyst system which can selectively activate the electron-rich donor, and then a separate catalytic system that can selectively activate the acceptor, and then combine these two to form these alternating copolymers. But then nevertheless, this result shown here, where we are seeing incorporation of the two monomers, is very, very promising. Next slide, please. So anyway, I hope that I've been able to show you that understanding the details of the polymerization allows us to create structures that haven't been accessible before. And the hyperbranch polymer example would be one example of that. And hopefully moving on, we'll be able to use direct arylation in order to access polymer architectures that weren't accessible before. But clearly there's a lot of work that remains to be done in achieving a controlled CH arylation polymerization. And also finally, a shameless plug. Next slide, please. A couple of years ago now, Seth Marder, who's also in the CH Center, we got together, wrote a perspective paper about synthesizing semiconducting polymers using direct arylation. And in that article, we go through the challenges that still remain in order to make this reaction work for us. So if you have a chance, please do look at it. And then next slide, I just want to end by thanking the people who did this work, specifically Lucian in the picture. He's the one in the red shirt in the middle. And then also Jason, who's just standing to the right-hand side of him. They're the ones who have been involved in the CH Center. So thank you, and thank you for your attention.